Today we're talking about a process that's eliminating plastic on Instagram and TikTok and blowing up all over the place called pyrolysis.
This machine here is my microwave pyrolysis reactor. It uses microwave heating to turn plastic waste into gasoline, diesel, jet fuel, natural gas, and solid carbon.
I'm going to tell you right off the bat, I am not a plastics expert.
Larry, I'm not an expert.
If you're a plastics expert, do me a favor, leave comments, your thoughts. I want to hear from you. We're talking to Julian Brown of Nature Jab. He's getting people to talk about plastic waste, elimination of plastic. This is somebody that's doing a hell of a lot more than anybody else out there to get the word out and get people excited about plastic elimination. So do me a favor, go on Instagram, find Nature Jab, let them know what you think about this episode. Let's get right to it. Julian from Nature Jab, Julian Brown. How's it going, man? How you doing?
Hey, I'm doing great, man. How are you?
Awesome. Sorry. So I found you on Instagram, scrolling through, and I see this guy, this wild guy, just like running around this backyard with this huge, looks like an atomic bomb. You know, you got like this huge piece of equipment, and you're making fuel out of plastic. One, how do you get started figuring out how to make fuel out of plastic?
It ironically all started with a Google search. So I was in high school. I was 17. I've been looking into the plastic problem for a long time, and I started to study deeper into recycling, what recycling is and how it works. And I realized that one of the big parts of recycling is that the plastic needs to be cleaned, right? And then that made me think, like, how can you recycle plastic that's dirty? The first thing I thought of was just burning it. But we know what happens when you just burn plastic out, right? Very toxic. So then I looked up, is there any other way? And then Google led me to this process called pyrolysis, right? And what pyrolysis is when you burn something, well, you don't burn it at all, but actually you're heating it in the absence of oxygen. So it's not burning it. What it's actually doing is it's using heat to break apart the molecular bonds of whatever's put in there. So that was how this started, just with a Google search.
All right, let's take a quick second to talk about idpdirect.com. Go right to that website, download the design guides, the sustainability guides, the recyclable icon guide, which basically lists out all the different icons. It gives them to you in vectors. You can drop them right into your artwork right now, today, and go right into production. All right, back to the pod. All right, so you're 17, you do a Google search for pyrolysis. I probably would have stopped there and see what else is on the internet, because there's a lot of cool stuff out there. But how do you go from a Google search to millions of people watching you building these machines that turn plastic into fuel in your backyard?
So that kind of was tied together with where I was, like being in high school. I was in a welding program in high school. So I would spend half the day welding my junior, senior year, and then the other half of the day just doing school stuff. But around that same time of doing my research on pyrolysis, because I've always been, very into the environment, gardening and all types of things, sustainable agriculture, all that type of stuff. Being a welder, when I found out about the process of pyrolysis, the first step I thought was, okay, this is how you do it, but is it possible to do that at a small or home scale? And I just looked up videos on YouTube, and there's actually a ton of videos of people all around the world, a lot of videos from people in India that just built really simple, small pyrolysis reactors that they use to deal with their plastic. And I was like, you know what? These people aren't even welding, and they're just putting this together. So I'm a welder, so I can definitely weld together just a small reactor just to see if it really works or if it's worth doing. So that's exactly what I did. I just put together a really small reactor, and then, it didn't work well, but it did work though. Yeah. And then that made me start to rethink, because for the longest time, I was always thinking like these types of things like are exclusively to huge companies or industries or plants or something, kind of like even the idea of like where we get our gasoline from and stuff. Like it's a humongous conglomerate. When I realized, wait a minute, I can not only recycle my plastic, but also turn it into these fuel products at home, I was like, this might actually really be worth taking serious. So I continued to prototype and build more and more designs. And then I started to broadcast it online when I started to transition into a more advanced or more sophisticated level of this. So I'll go into that. What pyrolysis is when you heat something up without oxygen, right? Now that heat could be anything, but the typical design is you have think of it almost like a pressure cooker, right? You have a pressure cooker, you put plastic in it, you close it, and then you have a fire under that pressure cooker or under that reactor container. That's how almost every design works, right? The issue with that type of design is you have a fire under it, or even if you had resistive coils on the outside, no matter how you put it, the heat has to travel from the outside of the container to the inside of the container, from the inside of the container, and conduct its way into the plastic, and plastic is an insulator. So there's a lot of heat and energy that's lost in all that transfer. So I had built about 2 or 3 of those traditional pyrolysis reactors that were heated up with a flame, and I realized those inefficiencies, and I asked myself, how could this be heated better? And I looked around the house, and I thought about different forms of heating, the oven, the pressure cooker, air fryer, whatever. I looked at the microwave, and I'm like, wait a minute. Microwaves, they heat really quickly. They heat from the inside out, so you're not heating the whole container. You're putting all the energy into the plastic, and they're very efficient. One of the most efficient forms of cooking, right? So then I realized that, and I was like, you know what? Let me implement microwaves into this if that's possible. So I built my first ever microwave pyrolysis reactor, which is where you utilize microwave heating to heat up the plastic in there. And at that point, that's the first ever reactor people saw online. That's when I started to broadcast, when I built my second ever, my Mark II microwave pyrolysis reactor.
So you built this machine that you're heating from the exterior and it's losing a ton of energy in the process, but then you build a microwave version of it, basically a microwave pressure cooker. I don't even like standing in front of my microwave when I'm cooking popcorn, let alone think that I can even build one. So just so that listeners understand, this thing is the size of a minivan. It's huge. It's a very large reactor. Like, yeah, you went to school and you learned how to weld. That's awesome. I wish I would have done that. But where do you go from learning how to weld to learning how to build these microwaves, like put this together?
Yeah. It's a very large reactor, and then it's utilizing currently 6 magnetrons, and magnetrons are what create the microwave. So that machine is the equivalent of 6 microwave ovens right now.
Where did you learn, besides the welding class, like where did you learn how to put all this stuff together?
Stepping into the microwaves was definitely outside my comfort zone, because being a welder, I just always been a super mechanical person. Like, I could build things. I used to always build with Lego blocks. But then when you start to tap into the microwaves, now you're getting into electrical, and now you're working with voltages that are lethal. So I kind of skipped all of the basic electrical apprenticeship and just went to right away to the most deadly voltages, right? So that took a lot of learning, and it was a lot of fear. In fact, to build my first ever microwave pyrolysis reactor, I spent the first almost year just getting microwaves from like a landfill that were thrown away, taking them apart, and then just playing with the parts in a safe way, like doing tons of research, watching tons of videos, but just like seeing how it worked and how I could integrate it, because I never messed with electricity before. And the number one rule I always followed was, when that thing is on, keep your hand the hell away from it. And then on top of that, even when it's off, they have a capacitor, a high voltage capacitor that will hit you really bad with electricity, even when it's off, if you don't discharge it. I've been hit with that 2 times before. You can feel the electricity go from one arm to the other, right? So even when it's off, it's crazy. So, that's really is what it was, right? Like, starting this to figure out how to build the reactors to begin with, it was just researching online. Then figuring out how to incorporate microwaves was just researching online. So it's just always been a matter of applying every type of research I could find.
Yeah, no, that's awesome, man. And then once you graduated high school, did you continue education, or are you just focused on this?
So once I got out of high school, right, at that point, I started broadcasting online. I had my second reactor, microwave pyrolysis reactor, and I took a gap year because I didn't know what I wanted to do, like if I wanted to go to university or not, because I already knew I was doing like something that universities do. In fact, that was a huge part of my research. Tons of university research papers on pyrolysis reactors at a lab scale in a university all over the world. But anyways, I took a gap year because I then I made my first ever TikTok video that summer I graduated. Yeah. And my first ever TikTok video I ever uploaded, it went viral. It got 1 million views, right? And so I knew, okay, not only am I doing this, but people are interested. So that really made me start to think, like, maybe I should start to pursue just this. I took that gap year and I built my Mark III pyrolysis reactor in that summer. And Mark III, at that point, was my biggest one. So my Mark II was literally the size of a pressure cooker. Like, you could hold it like this, right? Mm-hmm. Mark III was made out of a 55-gallon drum. So it started to get big at that point, right? It started, with everything, the bigger it gets, the more dangerous it gets. The Mark III reactor, before I could ever truly do a complete run on it, it blew up. Like it literally exploded like a cannon.
That's great.
So,
all right. So you have this barrel explode in your yard. What do your neighbors say? Are they like, "Oh my God, what's going on over there?"
To this day, I don't know what they think, but they ironically have never said anything, despite several small explosions and the house fire too. Well, almost a house fire.
Oh, man, that sounds pretty. It sounds pretty dangerous. Like this is like a no joke.
Yeah. It definitely is not the DIY friendly project.
If finding your spec data is a wild goose chase around your office, you've got a data problem. SpecRite is the only cloud-based management specification solution that every brand needs. Because if you don't spec right, you'll spec wrong. Okay, so what's actually happening in the reactor, right? You fill it with plastic and there's heat applied, and I get that there's a vacuum in there, but then what happens?
Right.
What's the benefit?
So what ends up happening is plastic is put in the machine, it's heated up without oxygen, and the first step is understanding what plastic is. Plastic is a product of crude oil, right? And being a product of crude oil, that means that it's going to have many of the crude oil components within it. In fact, if you look at the energy density of different fuels and compare them to plastic, plastic has more energy in it than diesel, gasoline, and jet fuel. So it's very energy dense, right? Comes from crude oil. So many of those same crude oil components are within the plastic because plastic is pretty much the solid form of crude oil, right? It's literally a solid. So when it's heated up without oxygen, well, if you heat it up with oxygen, you know what happens. It burns, and it burns really good because it has all that energy and all that fuel in it, right? If you heat it up without oxygen, well, those molecules that are giving it all the energy are going to break apart and form smaller molecules. So the reason why plastic to begin with is not biodegradable is because the molecules of plastic are super long. That's a great in terms of energy, but it's bad in terms of biodegradability because of super long chains cannot be broken down by bacteria and fungi and stuff, right? We put this in the machine, and then the heat breaks apart those super long bonds, right, into smaller bonds. And those smaller bonds end up becoming a vapor. And that vapor is essentially crude oil vapor. That crude oil vapor goes from inside the machine. There's a pipe system for it to come out of the machine, right? So those vapors leave the machine and they hit what is called a condenser. So those vapors come from the heated up plastic, so the vapors are hot, right? The condenser, the purpose of the condenser is to cool down the vapors. The vapors get cooled down by the condenser, and just like how if you take a water distiller or a water desalinator, right, it's going to form drips of water at the other end. The same thing happens when these vapors are cooled. It forms drips on the other end, but it's not water that comes out. That's the crude oil turning back into liquid crude oil. So that's gasoline, diesel, jet fuel, other liquids that are coming out from that cooled vapor. Just like how, condensation, when a cloud forms rain, we're pretty much raining the liquid hydrocarbons out of that crude oil vapor from the plastic. And then there's some vapors that never turn into liquids. They stay vapors forever. And those vapors are they're pretty much the equivalent of natural gas. And those are collected and compressed into a tank.
Now, plastics are famous for toxins like BPA, PFAs, PFAS, and so many other things in there that we hear about all the time. When you're processing these plastics, what happens to those chemicals?
Right. So that's a great point. So PFAS, forever chemicals. BPA, that's a big toxin in plastic too. What happens to these things? Almost every toxic part of plastic is actually an organic molecule. What does that mean? That means that things like the PFAS, the BPAs, those are able to be broken down by heat, just like anything else that goes in the reactor. It's all a matter of how hot the plastic is when it's being broken down. These things, like the forever chemicals in particular, do have very long chains. That's why they're called forever chemicals to begin with, because the chains take forever to break down. Microwave pyrolysis in particular has extreme hot spots of heat where the microwaves contact the plastic. So the heat is so extreme that even bonds of PFAS and such are separated apart. That brings me to another question that will probably be asked. When I do get these fuels out of the machine, right, on the other end, are there microplastics in the fuels, right? Well, to answer that question, that goes back to the same chemistry as well. For the vapors, the crude oil vapors to form from the plastic to begin with, they can only exist from the plastic being completely chemically destroyed. So for the liquid we get on the other end of the machine to even come out, there cannot be plastic in there because the liquid can only exist when the plastic has been destroyed, converted into that. It's a permanent chemical change. So there would not be microplastics inside of the actual fuel products from the machine. And then in terms of the more the chemical side of things, like the potential organic toxins that could be in the liquids or the gaseous vapors, that all comes down to analysis. You have to know what it is. For example, in the crude oil industry, the petroleum industry, we get crude oil right from the ground, and there's tons of toxins in that. But we have the technology nowadays to know what those toxins are and what to react to them with to get them out of our fuels. When you get it from your pump, it's EPA approved. So that's all the matter is. You have to understand what's in your product, and then you can do what you need to do to remove what needs to be removed.
Even under the high temperatures of pyrolysis, some of those organic compounds, they don't necessarily break down and disappear. I mean, they can break down further, but they turn into other compounds like phenols or bisphenols.
Exactly.
How are you able to test? Because you can't remove them all. And I mean, that would be another process to remove and refine further. How are you testing? How are you getting rid of that?
Right. Well, the good news about the process of pyrolysis is it is extremely controlled. Mm-hmm. Every single vapor and oil and everything that comes out is collected and captured. So there's no, I'm just emitting any toxin just out there. Nothing is leaving the system, right? So when it does come down to it, so the oils that come out the machine, it's like crude oil, right? It's a mix of gasoline, diesel, jet fuel. That needs to be distilled and refined to separate out those components. In the process of distilling, you're applying more heat, and you're also separating light fractions from heavy fractions. So in that process, if you have heavier things in there that have longer molecules, bonds that have formed, it's going to end up being stuck in the distillation chamber, right? So if I'm getting my gasoline out of my plastic crude oil, and let's say we do have some phenols in the oil, right? The crude oil. The phenols are not going to be in the gasoline because if they're heavier, they're going to stay in that crude oil. So when you get everything out, let's say you just have some sludge left over, right? Some sludge crude oil left in the distiller. You're like, okay, what do you do with that? And that has your phenols and all that in there. You put that back into the reactor, and it's going to crack it again. So you're going to keep cracking those molecules over and over again until they're broken down. Eventually, they'll be broken down into a complete permanent vapor like natural gas. And another good thing is this too. Since the process of pyrolysis does not itself emit anything, like everything is controlled and captured, the truth is this. Most hydrocarbons are the most toxic when released as is, right? Let's say there were some phenols in the liquid product. You go to put that liquid product in your engine, it burns the liquid product, and thus it will burn that phenol as well. But when it burns it and oxidizes it, it ends up the oxygen breaks it down to a different molecule again. So it's usually with almost everything hydrocarbon, it's less toxic when you actually do combust it. So that's a part of it as well. But like I said, the biggest thing is the distillation, because through distillation, we can have another process to further control what is in the products.
How are you protecting yourself? When you're running, are you running the equipment right now? Is it like running in the backyard?
Well, it's still in construction. I've been doing a lot of electrical things, but in terms of how do I protect myself when I'm running it, well, I do have a microwave meter. Like I said, it's the equivalent of like 6 microwaves on at once. So I make sure there's no microwave leaks, and it does good. It passes the microwave test. You could stand just 5 foot away from it, and the microwave meter is almost at 0. So that's great. The biggest risk of the machine is really electrical, because no matter how you put it, the voltages are so high, and there's so many sources of high voltages going into the machine that, if you touch the high voltage lines, or they had like a hole in them, or the wire starting to break apart, that could be dangerous. So that all comes down to making sure the machine is grounded really well, all the wires are covered super good. That type of safety stuff just has to be implemented. But other than that, once the machine, the electrical side of things is sorted, the machine is safe to run completely because, like I said, there's no emissions. You don't even have to wear a respirator around it when it's on. It runs off of electricity, so it's quiet, it's clean. And then on top of that, my current machine actually runs under vacuum. And running under vacuum means it runs under negative pressure, which means that unlike running under positive pressure, you have a risk of an explosion. A vacuum is quite literally the opposite. It's a risk of just sucking in a whole bunch of air.
It's like that submarine, right?
Yeah, it kind of looks like the Ocean Gate as well.
Yeah. You're putting plastic in here, using microwaves to break it down, turning it into some type of a crude oil. But you mentioned that it takes electricity basically to run this thing. So how much power does it take to run a cycle, and how much energy is contained in the fuel that you're releasing?
Currently, the Mark 4.5 is going to be a 50 amp system, meaning, and then the average run is about 5 hours, right?
Oh,
so it's consuming about, I would say, 10 to 11,000 watts. So over 5 hours, that's going to be like 50,000 watts. I have not done a full test run of my machine, the Mark 4.5 machine, because it's still being constructed. So I can't give you the numbers on how much energy we're getting out in terms of plastic for that much energy in, but I can give you the numbers on my past machine, the Mark 4. So Mark 4 machine was quite literally 3 times smaller than the Mark 4.5 machine. So it was 3 foot long. Mark 4.5 is 9 foot long. So in the Mark 4 pyrolysis reactor, for a 5-hour run, that's how long the runs would take for that machine, 5-hour run with 3 magnetrons on, it will consume 25 kilowatt hours of electricity. And in those 25 hours of electricity, through all the products that we got out, if those were to be burned, there would be an output of 48.8 kilowatt hours of electricity.
On average, I'm looking here, a house uses about 2 kilowatts per hour on average. So you'd be able to power like 12 houses. I don't know. I do terrible math.
Well, you have to remember that.
Oh, I guess
we have the fuels
on the old one. Yeah.
Yeah, like, because when you get the fuels out, like when I said we have 48.8 kilowatt hours, that's just the potential energy in the fuel. Once you convert that to electricity, you're going to lose at least half of it, right? Because just how things work, the internal combustion engines. So the goal is to get that number as high as possible, the output as high as possible. In terms of getting a higher output than input, that is actually a very common science in this process of pyrolysis. There's plants all over the world that already do this. There's research papers that speak on it all the time. But it's always been about getting enough out to where after you do the conversions and after the losses, you have enough to make the machine completely sustainable, self-sustaining.
What are you doing with the fuels that are coming out of this thing? Like, what happens to those?
I've been experimenting with my natural gas product. I would like to use a natural gas product to run a natural gas generator to run the machine. But another thing to do with a natural gas product is actually to use that natural gas you get to distill the fuels you get, the liquid fuels. And once I get the liquid fuels, I am in the stage right now where I'm currently putting them in engines and things for demonstration and seeing how they run, seeing how the engines clog up and gum up and all that type of thing. But long term, those liquid fuels could be sold to refineries. The raw crude oil could be sold as well. Or it could also be put into a generator to run the machine as well, or at least to supplement the energy consumption of the machine.
So before you put all the product in here, right? Because we talked about the energy that's required to run the machine. But before you actually put the plastics in there, are you grinding them down, or are you just collecting them and shoving them in there? Like, is there like a big Tide bottle in there, or is it like, are you picking the types of plastic, or is it just anything? Like, what are you putting in there?
So I do shred the plastics first because it makes the machine operate way more efficiently when they're shredded because there's not air in between it. The microwaves can heat it up better, and you could put way more in there at one time. So shredding is necessary. In terms of picking plastics, the machine will turn any plastic into fuel. It really just comes down to different plastics all have different molecular bonds and the ways how they're put together. So different plastics will give you different yields of fuels, different types of fuels. For example, a plastic bag might give you more gasoline, while a detergent bottle might give you more diesel, right? And then the quality could be different. Like one might have more waxes, one might have, it's super variable. And that's why, once again, I go back to what I was saying before, distillation is a must. Further refining the oils after they come out is pretty much a must if you want to be able to put it consistently into an engine, because there's just too many variables, even with the same type of plastic. If I were to put in just HDPE, high density polyethylene, the plastic that laundry detergent bottles are made of, right? I could do one run where the microwaves heat up the plastic completely uniformly the whole run, and I get out mostly diesel. And I could do another run where the microwaves heat up 90% of it uniformly, but 10% is not as uniform of heating. I could get out more gasoline than diesel. So there's tons of variables. So it's really hard to know exactly what you're getting at every time, but you definitely know how much you're going to get out. That's going to stay pretty consistent. So I might always get, like per 10 pounds of high density polyethylene, I could always get like 20 gallons of gasoline, for example, right? That's just numbers. I'm just saying it, right? And that will stay consistent. 20 gallons of oil. And then in that oil, it might be made up of half gasoline, half diesel, or more one or the other.
Sure. And I think, with as much plastic as there is in the ocean, with as much plastic as there is just sitting in a landfill, the idea here is that this is potentially, I guess, releasing that potential energy from the waste that we have and solving some of this plastic issue that we have. But then also, I've shared your Instagram page with quite a few people. I'm like, hey, check this guy out. This is doing, pretty cool stuff. And one, I think it's awesome that you've built this thing. Is there a team, or is it just you welding this thing together?
It's just been me the whole time. Crazy,
man. I hate to even change the oil in my own car, and you're over there making oil. so amazing. Some of the people that I've shared this with have come back with a couple of questions. They're like, all right, well, just ask these questions. And honestly, I can't even tell you what these questions are. All right. So the question, like one of the questions is, polycyclic aromatic hydrocarbons and heterocyclic carbon rings. These are some of the products that are produced from the pyrolysis process that are extremely toxic.
Right.
These are things that I wouldn't have asked because I wouldn't have known to ask. So again, some of the off gassing, some of what's happening in the process can be really toxic. So how do you to try to remove those things costs a ton of money because it's like a whole nother system and it's not super efficient. How are you able to, have you considered this? Have you figured out a separate process to remove this, or what are you doing to address those?
Yeah, so those polycyclics and the heteros, those are typically, they're going to be completely in that liquid product you get out, right? The gaseous product is usually pretty clean from all those things. And the reason why is what I was telling you before. It comes down to densities and fractions. So those polys and heteros, they're longer chains, they're heavier fractions. So they're always in the liquid product. The gaseous product is made of just super light fractions. So knowing that they're heavier fractions, once again, goes down to distillation. But we also know they're only in the liquid product. So that's good too, because we know now, okay, this is the product we need to make sure that we analyze above all else and do the testing. When you distill it, once again, you have to know what you're working with, what's in your fuel. So if we know we have some polycyclic aromatic hydrocarbons, well, we have to figure out what's their boiling point, what range do they come out in. So if their boiling point is that of gasoline, we know, okay, when we're distilling out our gasoline, we're going to have to either know that that's in there or utilize some type of method to potentially form a reaction with it, right? Or we could do this too. Let's say we know it's just in our gasoline fraction. Okay. If we know the polycyclic aromatic hydrocarbons are just in our gasoline fraction and we get that gasoline out, maybe instead of taking that gasoline and using it in an engine, you put that gasoline back in the machine, right? When you put that gasoline that has that toxin back in the machine, going back to what I was saying before, that the machine will crack the polycyclic aromatic hydrocarbons, right? And they will eventually just form the natural gas vapors that are the super light fractions that are not toxic. So you have to know what's in there and in what stage of fuel it comes out on. And vice versa, let's say the polycyclics were in our diesel product when we distill out the diesel. Okay, well then that means the gasoline and the jet fuel product are okay. They're clean of it. They don't have it. But the diesel product has it, so we just put that, instead of burning the diesel product outright, you just put that back in the machine. Because at the end of the day, all of these things, they're all known. They've been known about forever because there's all the petrochemical industry, and everything in there can ultimately be completely reduced and broken down with heat. Because at the end of the day, all these things are forms of hydrocarbons, right? So you can infinitely recycle it into the machine. You can mix it with the plastic, and ultimately it will eventually all break down into that natural gas product.
Just kind of thinking about pulling plastic out of the ocean, there's no issue using partially degraded plastics. The machine doesn't care.
Yeah, not at all. Not at all, because the truth of the matter is the partially degraded plastics, it has nothing to do with their energy content, just their quality. So they still have the same energy.
So what's the dream here?
So first of all, the first goal is people need to know about it. Whether it works like I want it to or not, or I achieve the goal I want, I truly believe that it's a crime that this technology is so well researched in science and it's been around for so long, and yet people are hearing about it for the first time through me, right? This should have been known. I truly believe that. So that's the first goal, and I believe that I am doing a great job at working on that goal. The second goal is I would like to implement microwave pyrolysis around the world at a big scale to deal with plastic waste, especially ocean plastics. And I say that because pyrolysis and pyrolysis plants have been around for a while, but microwave pyrolysis is rather new, right? In terms of doing it on an industrial level. In fact, to this day, there has yet to be a continuously operating microwave pyrolysis reactor at an industrial scale that's working right now, like in business. There's yet to be that anywhere. So I would like to tap into that and see, because pyrolysis has been around for a while, and then it's obviously not to the point where it needs to be because we still have ocean plastics, but we have not seen that with microwave pyrolysis yet. So I hypothesize that perhaps through microwave pyrolysis, it could be the key for this process, for this technology, to get it to the point where we truly have these machines at the point where we can get rid of this plastic waste once and for all. Well, the plant is considered almost like a recycling center because, once again, the plant itself does not emit anything. It just takes in it electricity. The only emissions come from when you burn the stuff. So it depends on what you're trying to do. Are you trying to sell the fuels? Are you trying to burn the fuels there and run the machine? Or are you just trying to take in plastic and get rid of plastic? That's going to dictate what type of permitting and legalities you're going to need for your plant, what you plan on doing with your products. Of course, when it comes to how I'm doing it in my backyard, I'm sure that violates every HOA contract ever, no matter how you put it. But on an industrial level, I have looked into the permitting side of things, but it really isn't all that complex with the machine because, like I said, it's kind of classified as just a waste facility because, as far as on paper, all you're doing is just taking in waste and turning it into something, but they don't know what you're doing with that waste until you say what you're doing. Or not the waste, but the process. They don't know what you're doing with what comes out.
So where are you getting all your plastic from?
I've been getting it just from my family thus far. Now, that has been okay with my past machine, my smaller machine, which is about the size of like a small dinner table, but this machine being the length of a long van,
Yeah.
I'm going to have to start accepting plastic donations and taking plastic from, my local gyms and things, because it's going to be consuming. I'll say it like this: my last machine would consume about my whole family's week worth of plastic within 1 to 2 runs, right? This current machine consumes it could probably consume my whole neighborhood's worth of plastic within 1 to 2, 3 runs because it just has such a bigger volume, right? And this is just at a backyard scale. So all I could think of is just imagine when this thing is humongous, right? So
Yeah.
I'm going to have to start accepting plastic donations, but I love that because there's a lot of people that, they know that plastic isn't being recycled like it needs to be, and then they feel bad to throw it away because they're like, well, this might just end up in the ocean. And I'm happy to give an alternative to those people that that know that they can send it to me and it will be truly recycled.
What's your Instagram? Where can people find you? How can they support you? And what's next? What are the innovations that are coming from Julian Brown?
Everywhere my socials are Nature Jab, Nature JAB. And what's coming next is I've been building this past machine, Mark 4.5, and it's almost complete now. Complete, with the electrical work, I'm on the last steps, and then it's going to be moved into a warehouse, and that's going to really start to change everything because once it's in the warehouse, everything is going to get better, the camera, recording quality, but most importantly, the presentation, it'll be open for tours as well. And then I'll be able to really get some good data on the machine in terms of all the numbers that everybody always asks for, like the energy and all that once it's complete and in the warehouse and such. And once that machine is built and we get the good numbers, and then we're going to do some amazing things with the fuel products, like we're going to run all types of vehicles, cars, hopefully some planes and boats, really exciting stuff. Once that's been set, then it's going to be time to start transitioning towards Mark 5, the first ever industrial machine, or the first pilot plant. So it's going to be the biggest machine, the most professional machine, and most well-done machine, and it's going to be the first plant that will prove this technology's viability on an semi-industrial scale.
Are you making money on this? I'm just trying to think, like, dude, that's going to require some funding. Like, so is the Mark 5 and everything you're doing on social, is that generating income?
Yeah, so the machine itself is not generating income because right now I'm just taking in plastic. I'm not doing anything with my products in terms of selling them or anything, right? In fact, I'm sure that would be illegal with all types of permits anyway, and also analysis, right? So currently, the Mark 4.5 has been completely crowdfunded. So I always, extend my gratitude to every single supporter because everybody made this possible. It's truly my dream to do exactly what I'm doing now, to just put all of my energy and focus into building these machines. And everybody has made that possible by the support. So Mark 4.5 has been crowdfunded. Mark 5, my idea and my goal for that machine is going to be something similar. Now, I'm not close to the idea of investors and such, but at the same time, I do always look at how lucrative things are online when it comes to like virality. Like, you could have a viral video and you can, if it's big enough, you could literally make 6 figures off of a viral video, right? And I think about that and I'm like, well, the machine is only going to cost about $1 million. So in theory, if I can make enough viral videos, I could just have the machine once again crowdfunded just off of the attention of the people. And I think that's kind of beautiful because I think that one of the biggest differences between what I'm doing and just anybody else or other companies is the fact that I am just an individual, and the fact that I did start this in high school and stuff, and that I am, I guess you could say a spokesperson for people, given that I'm just a person myself. I'm not some conglomerate, some type of entity or company. So I think it's kind of beautiful to keep it in the power of the people in that way, at all stakes possible. Like if it had to come down to changing up the course and getting an investor, going down the typical company route, it's okay. The goal is to get the plastics out the ocean. But if we could keep it in the power of the people, I think that's beautiful because that's how it started.
That's awesome, man. All right. So then go check out Julian at Nature Jab on all the socials. You can check out the machine. You're going to be blown away by what he's actually built. Maybe you're inspired somebody to make something in their own backyard.
Hey, thank you for having me so much. It was great being here.